international cooperation at its best. So we are getting closer now to the next big moment, which will be the beginning of what we call the synchronized sequence, or the automatic sequence. That's the last 4 minutes of the countdown. That's coming up in about 1 minute, Irene. That will be a big milestone.
Yes, we will gradually give the launcher the full autonomy to proceed with liftoff. Computers will be managing a complex sequence of operations. This involves several steps, including loading takeoff time, flight program software into the onboard computer, and inertial platform initialization and alignment procedure. It is the handover between the ground control and the onboard computer. Just a few seconds before liftoff, the flight program software will take control of the launcher.
So that's what happens during the synchronized sequence. That's coming up now. There'll be a lot of vital operations happening during that time, won't there?
Yes, it's a very complex sequence of operations. All is timed to milliseconds.
À tous de DDO, attention pour la séquence finale lanceur.
Today's launch. So we have a number of control rooms on the job today. We saw them earlier. Obviously, we've been looking a lot at mission control. We fondly call it Jupiter here at the spaceport. The teams at mission control overseeing the whole mission. And then, of course, we saw earlier launch control. The launch controllers are very much concerned with the rockets and the pad and all those preparations prior to launch, Irene. I mean, what are they doing in there?
Yes, the launch control center is called Pandora. Probably is a reference to the mythological figure of Pandora box, symbolizing the transition from a sealed, controlled state to the complex and powerful deployment of a mission. The teams here are in charge of preparing the rocket and checking it. They monitor all these final operations before liftoff. And of course, after liftoff, the rocket goes on autopilot. The teams inside Pandora are three. There is the technical authority team. They define the launcher and specify the way it is operated. The operational team. They conduct and coordinate all the activities, strictly following procedures prepared by the specialists. And the quality team. They ensure that everything complies with the stringent standards required for a safe and reliable launch.
And we also have a control room working in parallel in Colleferro, which is where your HQ is at Avio, just outside Rome.
Yes, it is the so-called base arrière. They are checking the launcher's behavior in parallel. They are analyzing data and watching every parameter, every reading on the launcher. All these people come from different teams, such as propulsion, structures, control, and they are ready to jump and support in case of need. This is our rocket, and today we are launching it.
You must be feeling quite emotional. We're getting
Yes.
close now. 1 minute and 42 seconds to launch and counting. Vega standing tall on its pad with its lightning masts around it. I guess this can be quite a tense moment.
Yes, I think concentrated is a better word. It's really emotional, even if they are done so many times, each time is so unique. Right now, the boards are green,
À
and
tous de
everything
DDO,
is ready.
attention pour moins 1 minute. Top, H0 moins 1 minute.
We are 1 minute to launch. We're live at the European spaceport in French Guiana, and SMILE is about to begin a journey that will change how we see Earth's magnetic shield forever. Good luck, everyone.
Buona fortuna.
À tous de DDO, attention pour la séquence finale. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, top. Allumage P120 et décollage. Propulsion nominale, début du basculement. Fin du basculement. Tous les paramètres à bord sont normaux.
We have liftoff. Smile has started its journey on board Vega C, lighting up the night sky as it flies above the European spaceport here in French Guiana. The range operations manager telling us that the propulsion is nominal. We are heading northeast out over the Atlantic Ocean, and we can hear the rocket now in our commentary box. It's taken this amount of time for the sound to get to us. It lifts off so fast, doesn't it?
Tous les paramètres à bord sont normaux, la trajectoire est nominale.
And we're burning the P120 at the moment, the first stage.
Yes, the name comes from 120 tons of propellant, but now it's fatter, it's 140.
It's gained weight.
However, he has a very thrust-to-weight ratio, so its thrust is double the mass.
Propulsion
So
nominale,
we
la
have 2 g of
trajectoire est
acceleration. This means twice the value of gravity.
And we've passed something called the transonic region. What's
Yes. Yes, the vehicle is now quicker than the sound, the velocity of sound, and now is in supersonic
Propulsion
region.
nominale.
He's telling us that the propulsion is nominal, everything's going well.
La
We can
trajectoire est
see
nominale.
Yes.
our rocket in the
Yes.
night skies here. We can still see that P120 engine burning.
Yes, we are towards tail-off, so the stage separation windows is open, and we are waiting for the separation command.
Séparation du P120.
We have
Allumage
confirmation
Z40.
there from the range operations manager that we have separated the
La propulsion est
first
nominale.
stage, the P120, and ignited the second stage, the Z40, and he's telling us that propulsion is nominal. We've reached Mach 6.
Trajectoire
Yes,
nominale.
now we are 6 times quicker than the sound.
And we've started what we call the dogleg maneuver.
Yes, the dogleg is the name of coming from the shape of this maneuver. It's a very steep
Tous les
maneuver,
paramètres à bord sont
and
normaux.
it's done just after the ignition of Zephyr 40 because you have very low loads, aerodynamic loads, and so you can also do maneuvers very, very steep. And this normally due for safety reasons like geographical constraints or visibility constraints.
And we're burning the Z40, the second stage.
Yes, and now we are also protecting. We have also from with some seconds we will be so high that we will be able to release the fairing, because the fairing
Propulsion
is
nominale,
useful
trajectoire
when you
nominale.
are in the lower part of the atmosphere. When the density is decreasing, you can release the fairing.
And we get a very good shot there of the fairing. This is our animation of what's been planned for the journey. You can see the fairing is that bulbous section.
Yes.
The front of the rocket, the top of the rocket
Yes.
is containing our satellite. And as you
Yes.
say,
It's very important because it protects the Smile from aeroacoustic vibration at liftoff and from friction during the lower part of the atmosphere, and it protects from aerodynamic loads and also on thermal loads.
Trajectoire nominale.
the
Séparation
trajectory on the
Z40.
left-hand side, the green line is the planned trajectory, the yellow line the actual trajectory, and that's
Allumage
how
du
it
Zephyr
looks
9.
when we lose the Z40. And he's
Séparation de la
confirmed that we've switched on the Z9, the next stage, and we have jettisoned the fairing. As you say, we're now in space
La propulsion
effectively,
est
and we
nominale.
don't need it anymore. And he's telling us the propulsion is nominal. So we are now burning the Z9, the third stage, the Zafiro 9.
It's a very powerful stage. During this phase, the speed goes from 15,000 to 27,000 kilometers per hour. That is about 30 times the velocity of a commercial aircraft.
That's fast. And we can see SMILE, it's the gold structure. It's actually now exposed to the cold vacuum of space for the first time. Can you just talk us, say, from right to left, Irene, what we're looking at? On the right-hand side, obviously, we can see the engine burning, and then the white structure in the middle.
Yes. Sure, Katie. The white part is the motor, so the Zafiro 9 and the Avum. Then you have the black conical structure that is the payload adapter. This is to support the payload and also to push it when we are reached the target orbit with a gentle release with 4 springs. And the gold is obviously the satellite that is protected with a cover for thermal protection.
And the gold stuff is the thermal protection. And these, as I mentioned earlier, these are computer-generated images. They are showing us a simulation of what's been predicted for the launcher in real time. So it's not actual camera footage from space, but it gives us a great view of what's happening, a visualization. And these are the tracking stations, Galileo in French Guiana and the tracking station at Saint-Jean-du-Maroni.
La propulsion est nominale.
We have twisted and facing upwards. Why is that?
Yes, this is the so-called neutral axis maneuver. It's performed just before the separation of Zafiro 9 to orient correctly the Zafiro 9 before separation and make it re-entry in a predefined zone.
And just briefly, we've also started something called closed-loop guidance.
Yes, you are right. And during Zafiro 9, we have the so-called closed-loop guidance. That is a guidance that recomputes on board the desired trajectory, considering the actual state of the launcher.
Séparation du Z9.
So it keeps us on track.
Fin de visibilité de Saint-Jean.
And we've separated the Z9. It's burnt its propellant. It's done its job. We don't need it anymore. And we are now, there again is a good view of our tracking stations and our flight path. So, Irene, right now, at this point, normally we would switch on the upper stage. The upper stage is that white disc that you can see there. But we're not doing that today, are we?
Yes,
why is that?
Indeed. That's right, because SMILE is quite different from a sun-synchronous orbit mission. And so we have to wait about 13 minutes in coasting phase before igniting again the Avum. And in this phase, the launcher is just controlled by roll and attitude control system.
So we're in a coasting phase right now. And actually, we've got a good view of SMILE now, and you can see that it's actually got a very bulbous shape to it. That's sort of the gold structure being kind of very, very bulbous. It's the only way I can think of to describe it. And that's actually the fuel tanks, isn't it?
Yes.
And we've got a lot of fuel on board because we're going a long way. We've got to travel a third of the way to the moon. It's a long way.
A very long journey. So after the launcher release, the satellite will have to travel a lot, up to 120,000 kilometers of apogee and 5,000 kilometers of perigee. And so to do this...
Apogee being the furthest away, perigee being the closest to Earth.
Yes, you are right. And to do this, it has to perform several racing orbit maneuvers. And to do this job, this propellant is needed. We have almost 1,600 kilograms of propellant here. That's a very big amount for a satellite.
That's a lot of it.
Yes, you are sure.
And so did the fact that it's carrying so much propellant on board, did that give you any challenges in terms of designing the mission?
Yes, a lot of challenges because the fuel sloshes. So we have to be very careful in order to check that it doesn't interact with the launcher dynamic. So this is why it's important to simulate and verify every detail.
Well, you've done some very good work in doing that. And if you just look at your screen there on the left-hand side, you can see there on the animation that we are actually twisting very, very slowly. So effectively, we're barbecuing. And that is the technical term.
Yes, you are right. This is the barbecue, and this is used to avoid having the solar that is facing always on the same face. So with the barbecue, we can have the same constant temperature across the launcher.
Indeed, we're
All
barbecuing
around.
as if on a spit, rotating. Right, now, once Smile gets to its vantage point, it'll be able to look down and image the full sunlit edge of Earth's magnetic field. It'll also photograph the northern lights, which is rather something because no mission has ever done that before. And here's the thing, it'll give us actual images of Earth's magnetic shield reacting to the solar wind. That's quite something because the magnetosphere is invisible to the human eye, so this is a completely new way of seeing our planet's protective bubble in action. I'm absolutely delighted that joining me is the Director of Science at the European Space Agency, Carol Mundell. Carol, thank you so much for coming up to see us in the commentary box.
Thank you, Katie. It's great to be here. I'm just catching my breath.
Hang on a sec, I'm just switching your microphone on. Yeah, I was just saying thank you so much for being with us.
Thank you, Katie. Thanks for having me here. I'm just breathless from that absolutely spectacular launch. I mean, we're all stunned. And it was such a beautiful view out there on the terrace and the clear night sky. We just saw it for many, what felt like many minutes. But
It was incredible. It really lit up the sky, didn't
really
it?
did. It was fantastic. So congratulations to our launch teams. They've done a great job so far, and long may that continue.
Yes, indeed. Let's see how we go. 11 minutes and 32 seconds into launch right now. So, Carol, let's just talk about SMILE. Let's talk about the magnetosphere. Let's start at the beginning and just explain to anyone who's not familiar what is the magnetosphere.
Yeah, so the magnetosphere is actually the Earth's magnetic field. So we think at the center of our planet is a liquid iron core, and that produces a magnetic field, a large-scale magnetic field. Now, what happens to that magnetic field is it's actually shaped by the solar wind. So we have an Earth-Sun system, and the sun produces radiation and flows of charged energetic particles, and that actually shapes our Earth's magnetic field to make this protective magnetic bubble that, as you said, protects our planet and actually makes life on Earth possible. Otherwise, we would be toast.
Yes, which wouldn't be a good place to be.
Not really.
So effectively, then the particles from the sun, they kind of bounce off the magnetic field and they fly off into space and they go around us.
Some of them do, and that's one of the big questions that we'll use the SMILE mission to answer, because obviously at the front, the sun side, the daytime side, we actually have what's called the magnetopause, and then at the back there's a magnetotail, and actually some of those charged particles sometimes leak down through the weaker magnetic field particle edges through magnetic reconnection, and that then produces the aurora and the interaction right down to the ionosphere, which is actually where the SMILE acronym comes from, because it's that solar wind magnetosphere ionospheric link explorer, which is actually what SMILE means as an acronym, and we have other reasons for calling it SMILE too.
So what's SMILE going to do, and what's it going to tell us? Where's it going to be, and what's it going to do?
So what SMILE's going to do now, obviously, it's on its way on the rocket, and gradually it will actually be released, but it will then continue actually to be, over the next month, will reach up to 120,000 kilometres above the North Pole, so it'll be a very elliptical orbit. It will swing down 6,000 kilometres above the South Pole, download its data, and that will be the orbit for the next 3 years. And it will be a revolutionary transformational mission, as you said, for the first time making the invisible visible, but actually that continuous monitoring of the dynamic Earth-Sun system, taking those first X-ray images, continuous monitoring in the ultraviolet of the aurora, and then also we have two other instruments on board that will make direct measurements of the Earth's magnetic field to compare with the X-ray images, and a direct probe of the particles that are reaching Earth. So for the first time ever, we'll have a global system view, a dynamic view of cause and effect. And ultimately, although that's incredibly important for our scientists, and our scientists will do their work, they will pass their knowledge and insight onto more operational teams who care about space weather and the predictions for geomagnetic storms that arise when the sun goes into its most active phases and really starts to impact our Earth system.
And it's not the first spacecraft, is it, to look at the magnetosphere?
It's not, and actually we have a long pedigree. So over 20 years ago, we launched the cluster mission on an Ariane 5, actually, from Kourou. And that was the first time we had 4 spacecraft, which was very revolutionary at the time, taking the first 3-dimensional data of the Earth's magnetic field. Also, our Chinese colleagues had the double star mission, and again, making those point measurements and giving us a little glimpse of what that system is about. We also have our solar missions, such as Solar Orbiter, which is really studying how the sun works and what's coming from the sun. So for the first time with SMILE, we'll be able to put all of that together and have an unprecedentedly complete global system picture.
And this has been quite an amazing collaboration, wonderful collaboration, hasn't it, between the European Space Agency and China?
It has, incredibly. I mean, way back in 2005, ESA and China signed in a cooperation agreement. So that's really the framework that lets us work together. But of course, how do we want to work together? What do we want to do? So we've had some collaborations, for example, like Cluster Double Star. We've also provided some instruments for Chinese missions, most recently Einstein Probe, to study new black holes in the universe. But this is the first time, and it was really very revolutionary to think about how we would devise bottom up, asking our European and our Chinese scientists to come together to propose a mission that would be devised, built, implemented, and operated 50-50 between our two communities.
And what kinds of discoveries are you hoping for? I mean, what makes you all feel excited at the moment?
I mean, as I say, I think, I'm a scientist by background. I've worked on magnetic fields. They've always felt a bit of a niche. They're always hard things to explain. They're always incredibly fundamental, but very difficult to study and to understand. So to suddenly be able to make images, to take X-ray images, to take the legacy of things that we've done on other missions within ESA, such as XMM Newton, one of our X-ray missions, take that technology and bring it into a new sphere. But it will also be measuring the interplanetary magnetic fields and disentangling those. So I think the science will be fundamentally breakthrough. But for me also that real world impact, because at the moment we do have models of what might happen if there is a solar storm, how it might impact our satellites or our ground electrical subsystems. But the predictions are not accurate enough yet for operational use, because we miss this complete fundamental understanding of the whole system. So those little glimpses that we've had don't constrain the models well enough. So for me, I think we're going to see a big step forward also in the operational protection of our planet from space weather.
And just briefly, before we go, Carol, just talk us through some of the exciting things ahead in the future.
Yeah, I mean, it's so exciting to be here, Katie, for SMILE, because obviously we have so many missions coming through in our ESA program. We had our ministerial conference last year where our 23 member states came together and uplifted the science budget as a vote of confidence in the quality of the program. We celebrated our 50th anniversary at ESA, science program 51 years old now. And so actually we're answering some of the biggest questions. Why are we in the universe? Is there habitability? Are we alone? What's the nature of the universe? So we have a new mission that we will launch next year to look for Earth-like planets around sun-like stars, so solar systems like our own. We will then launch the Ariel mission, which will study the atmospheric chemistry of 1,000 planets and other solar systems. And then we will go right out to our LISA mission, which is the world's first ever gravitational wave interferometer to actually sample the nature of space-time itself. So from habitability to life out there, right through to the nature of space-time itself. I mean, it's an exciting time we have ahead.
Wow. It really is, isn't it? Watch this space. It's wonderful. Thank you so much, Carol.
Thank you.
Thank you very much for coming and talking to us, and good luck with the rest of the mission.
Thank you.
So to get SMILE to its all-important vantage point in space, we need to start by parking it in a temporary orbit close to Earth. That's where we will inject it into space, and it's going to take us about 40 minutes to get there from here. We'll need to ignite the Avon Plus upper stage twice during that time, and the first firing is scheduled in a couple of minutes' time. So, our flight path, Irene is back with us. Irene, where are we?
Yes, now we are still flying over the Atlantic Ocean. The launcher then will pass over Northern Europe, then across Russia and China and South Asia, reaching Australia when it will be ready to deliver the satellite. And then we continue back towards South Pacific and North Atlantic up to the orbiting when it is over Iceland.
And we're tracking the rocket using telemetry. From the moment it leaves the pad, there's a network of ground stations watching its flight. Basically, the rocket's what is effectively communicating with us, isn't it?
Yes, that's the ground station. It's how we can communicate what is the status on board. So it tells us, for example, how the engines are performing, the fuel that is left, the temperature, the exact
Acquisition
position.
de la télémesure par la station Svalbard.
He's just telling us that we have picked the signal up now at the tracking station in Svalbard, which is a Norwegian archipelago in the Arctic Ocean, roughly halfway between mainland Norway and the North Pole. Yes, what you were telling us about the telemetry.
Yes, it allows to
Les
track the
paramètres à
flight
bord
in
sont
real
normaux.
time. And telemetry is how we know if the rocket is healthy.
So we are coming up now on
Allumage
the
de
next
l'avant.
moment. We have confirmation from the range operations manager
Propulsion
that we
nominale.
have switched on the engine on the upper stage and everything's going normally and going well. So the Avon Plus has now taken
La
the wheel
trajectoire est nominale.
for the next leg of the mission. And it has a very important job because it has to transport Smile to its injection orbit where it will then be released into space. So this is really where Smile's journey gets interesting, isn't it, Irene? It's a very sophisticated piece of technology.
Indeed. Avon Plus is very accurate and also flexible. It's accurate because it is due to the thrust control and a very accurate cut-off impulse. The flexibility
La
is linked
trajectoire et la
to the...
propulsion sont nominaux.
The flexibility is due to the fact that you can ignite it several times, up to 8 times. So you can really deliver a satellite and then continue your mission to deliver other satellites.
Yes, because sometimes you do have more than one
Yes.
satellite on the same rocket.
Yes, it is not this case because Smile is a single payload mission, but in other missions we had released several payloads in different orbits. It's like a space bus.
Dropping off at
Propulsion
different bus
nominale,
stops.
trajectoire
A
nominale.
quick word about our speed. We're travelling at 7.39 kilometres per second. It's very fast.
Yes, 30 times faster than a commercial aircraft.
So as the tracking stations collect the data from the launcher, they relay it to the teams here at the Guyana Space Centre. We saw them earlier. We can see them on the left-hand side of the screen there, focusing hard at this point. It's called the Quick Look Telemetry Team, or the CVI. What are they doing?
They are receiving real-time data from the launcher about propulsion, control and trajectory, and this allows them to monitor the launcher's
L'orbite
behavior.
atteinte par le lanceur est stable.
And they can, of course, confirm if the satellite is separated as planned.
And Irene, for the first ever Vega flight back in 2012, you were in there, weren't you?
Yes, you're right. I was in CVI 14 years ago, so in 2012, for the first flight of Vega. So it was really impressive for me to have this dream becoming reality, because I was seeing all our simulations that were really becoming true in our screen.
How wonderful. And they have their own internal comms loop, so they pass the information of the confirmations and the milestones to the range operations manager, and who then announces those confirmations to the base. So we are now getting closer to switching off our engine. How does it know
La
when to switch it on
propulsion est
and off?
nominale. La
Yes, the upper
trajectoire est
stage
nominale.
has its brain, that is the onboard computer. So it's what brings the launcher to life. Without it, the launcher will be just an amount of structures, propulsion, wiring, without no way to function as a system. So this is why we can have a real mission from liftoff to the orbiting, thanks to the onboard computer.
So how does it actually execute that mission then? I mean, how does it know where it is, what it's supposed to do?
Yes, the functions that are inside the onboard computer, the main functions is the navigation, guidance, and control function.
Well, that's your speciality,
Yes.
isn't it?
The navigation provides you the positions and the attitude you are sensing through your inertial measurement. The guidance provides you the desired trajectory to be followed, while the control tracks the trajectory to be followed
Tous les
thanks to
paramètres
the
à bord sont
actuators.
normaux.
So the thrust vector control and reaction control system.
So this is the
Extinction de la
moment we switch off the engine on the Avon upper stage. We have that confirmed. And so we have now entered, again, another ballistic phase. That means we're traveling without propulsion. We are coasting without the engine. So we're about 25 minutes now into the flight, but of course the teams have been working here at the spaceport for weeks and weeks getting the rocket and the satellite ready for today's launch. We call that process the launch campaign.
Yes, we can run several launch campaigns in parallel here at the European spaceport. This is very good for our customer because we can increase our launch rate.
barbecue.
He's just telling us that we're orientating for the barbecue mode. So the parts of Vega C are built in Italy and transported here to the Guyana Space Center where they're assembled. What's been happening during the launch campaign?
Yes, the Avon upper stage and the shell of the first stage, the P-120, arrived on board of a sailing ship called Canopy. The P-120 was then transferred to the launch zone slowly using a special
retain only one, I would refer to the team excellence, the team motivation, the team spirit, which is very important, especially when you have people from different cultures.
In this mission, I have to verify that operation adds no extra pyrotechnic and safety risk and adds no extra exposure for the workers. My role is to bring safety rules into reality. When risks are mitigated, we can focus only on the flight.
Our engineering team works hand in hand with our partners from Avio in such a way that we respect the right level of quality, from the mission preparation to the manufacturing of the stages to the integration until the launcher is ready on the pad.
My most important responsibility is ensuring coordination across all teams. So I focus on the strategic decision making to keep the ground availability aligned, safe and efficient.
When we see Vega on the launch pad, we have a sense of pride and satisfaction of the work done. But at the same time, we have to be cautious and content because we have not yet completed the mission. And only when we see that the spacecraft has been released on the right orbit, we leave way to our joy.
It's a powerful mix of responsibility and pride. You feel the weight of every decision,
Fin de
but
visibilité
also a glistance of achievement, knowing the efforts of all the teams comes
attendu
together
de la
in that
télémesure
final
pour environ 22
Rocket
minutes.
is extremely powerful, and you put on top your satellite that you've been working on for 10 years, and then you send it to space. So of course it's extremely exciting, it's super exciting.
I feel like I do the best job in the world. It's a mix of focus and pride. We turn sweat into emotion.
But it's also a little bit sad because you are basically saying goodbye to the child that you've been working on with the hundreds of people in your teams in China and Europe, and it has to accomplish its mission, which it is designed for. So I'm sure it will be all okay.
Oh, so much passion, so much dedication. Right, we are going to take a break. We're going to be taking a break for about 16 minutes, about a quarter of an hour. So we'll come back to you at 1:39 a.m. here in Kourou. That is 4:39 Universal Time. That's 6:39 in Rome, Paris, Central European Time, and 12:39 p.m. in Beijing. See you back here then. Don't go away.
You.
This is really a milestone. It is really a milestone. It is really a milestone. Can you hear me?